eigenstates of the operator Q, which corresponds to some physical quantity. This means that Qi is, say, BI. So this is the meaning, right? And then Q acting on F is BF. So the first. Second, let us assume that Hamiltonian is invariant with respect to symmetries associated to Q. So Hamiltonian is invariant with respect to symmetries generated by Q. The physical quantities are generators of the symmetry groups, as we discussed before. So this means that Hamiltonian commutes with operator Q. Right? This is expression of the symmetry of the Hamiltonian. And suppose that Hamiltonian H provides a transition between I and F. So this then, as we did before, last lecture. Okay, so let me repeat. I and F are eigenstates of Q with eigenvalues I and F. So Q can be isospin, for instance, third projection of isospin, or electric charge, or some other characteristic, strangeness, etc. Okay, so this is the first, and these states I and F have certain eigenvalues with respect to Q. Hamiltonian is invariant, and then we are exploring the property of this matrix element. So I is transformed to F. So what we are doing, we take this equality in between the states F and I, Q, H minus HQ, initial, and this is 0. And then due to this feature, we have this part, which is BF, F. And this term is BI and I. And so what we will get is BF minus BI. And here F, H, I. And that should be 0. So this means that F, H, I is non-zero only if BF minus BI is 0. So which means that BI and BF are equal. So which means that this quantum number is conserved in the reaction. So the matrix elements are non-zero, and therefore the transitions exist only if you have equality of this BI and BF. So now I will start to discuss various symmetries, and the plan will be the following. As we said already, to define the symmetry means to define transformations. So in all the cases, we start with definition of transformations. So then we check invariance or symmetry or invariance. Mostly Lagrangian with respect to these transformations. So if Lagrangian is invariant, then we have the symmetry. And then the third, we will discuss physical consequences of the symmetry. Now, how we define transformations? In principle, you can try everything. So you can invent your own transformations and then check all the things. So of course it's interesting if your Lagrangian is invariant. So you may introduce some transformations with respect to which Lagrangian is not invariant then, so nothing to do. However, in some cases you may get this invariance. And then you can check what are physical consequences. Very often we are introducing transformation using some physical input. Again, you may ask why we introduce transformations in this way or in another way, and the answer is that you can try different versions and then to see if you have invariance or not. So we start with parity.
Discuss on the discrete symmetries?
Well, I will discuss, again, what I will discuss is parity, which is there is symmetry, CP, and that symmetries are related with U1, which is continuous. Okay. And then you can, if you want, to generalize this to more complicated symmetries. So, parity. And we start with our definition of transformations. So first, transformations of coordinates. Under P transformations, x go to minus x, y go to minus y, z go to minus z. Or you can write this as r vector go to minus r. This is equivalent to just making this change of the sign of one of the coordinates, and then you can get the same if you do rotations in addition. So that is equivalent to just z go to minus z plus rotations, and then you get the same result. Now, other quantities, momentum is transformed as with change of the sign. Energy doesn't change. And then the question which will be important for our further discussion is how angular momentum changes. So how angular momentum changes under P. Tell me. Transformation. So how angular momentum changes?
It doesn't.
So it doesn't change. And it looks like a bit strange, right? Because you have some vector and then you turn coordinates and you expect that that vector should change the sign. On the other hand, the angular momentum is given by vector product of momentum and radius. Both change the sign, the product doesn't, right? So how to reconcile these two things? And this is important, right? So you need to understand. So on the first side, since you have some vector, it should change the sign. On the other hand, it's vector product of two other vectors which do change the sign, and product doesn't. So how do you understand this?
Because it's a pseudo-vector, not a vector.
But so what? It's just... So why pseudo-vector should have such a dependence?
Of the epsilon ijk in the vector item.
Well, this is kind of formalism, but what is kind of physical reason for this? The point is that definition of angular momentum is our convention. So we introduce this vector as a convention according to certain rule. So let me remind that if you have coordinates, let me see, x, y, and z, what we are saying that the vector L is in this direction of z if the motion occurs from x to y, right? Rotation. So this angular momentum is related to certain rotation. Okay? So, and this is our kind of convention, that we are saying that L is along z if rotation is from x to y. Now, if you change, if you make P transformation, then what you will get is, so z will be this, here will be x, and here will be y. And rotation doesn't change, it's again from the x to y. So when you do this reflection, nothing changes with your rotation, because this is something which is moving in the plane, right? And if you look from this and from that, it's the same rotation. So here, in this case, according, again, our convention, we say that L should be in the direction of x. Sorry, z, right? So this is what's going on. So here, L is in the direction z, or increase of z. And here is also in direction of increase of z. Clear? So again, P transformation doesn't affect your motion which is in the plane, right? So if you change from this coordinate to that one, nothing is changing, right? So you have the same rotation. And again, L is this is direction of L is our convenience, right? So this is how we decided to do this. But the direction doesn't change, and therefore L shouldn't change. So again, it's a rotation in this way, and it's again still from x to y, even if you change z to minus z. And the rest is just our definition. So we are defining direction of L in this way. So this is the meaning, right? So what is important that that reflection doesn't change your rotation, still from x to y. Now, helicity doesn't, what happens with helicity? And helicity is projection of spin on the momentum, right? So that changes the sign, because P changes the sign, and spin, the same actually is for the spin. Spin doesn't change, and therefore helicity changes the sign. This is helicity. So this is how we define these transformations of coordinates and related stuff. Let me add more. How current is transformed under P. For current has four components: zero component and vectorial components. And under P transformations, zero component doesn't change the sign, while vectorial components get minus sign. This is how we introduce transformation of current. This is similar to what we have with momentum and energy. So this is for vector, and energy and momentum is for vector, and it has the same type of transformations. So now let us discuss how fields are transformed. And we start with scalar field. Scalar field. F T under P transformations. Of course, we change the sign of the coordinate here. It will go to F minus X T. But here, in general, we can put some factor at the P. And this at the P can be plus or minus 1. Why? Because if we do twice P transformations, then we are back to initial state. So after double transformations, our X T dependence doesn't change. But we will get this at the P squared. F X T. And therefore, since we are back to the same state, then this eta P squared should be 1. Okay? And therefore, eta P can be plus or minus 1. So this eta is kind of internal characteristic. So here, in the case of parity, we have entanglement of some internal change and exchange of external coordinates. So this is what we call parity of particle. And what is interesting, that nature realizes both possibilities. So if eta P is 1, so we are saying that this is scalar. If eta P is minus 1, it's pseudoscalar. And we have particles like pi, eta, k meson, so all they are pseudoscalars and they change the sign under P, under reflection of coordinates. Particles like rho meson, F0, K star 0, or K star. So they are, so that should be, it's rho star, but let me see, K0, X, C. So there are also such mesons which do not change the sign under reflection of coordinates, and they are scalars. So clearly the Lagrangian, or free Lagrangian of the scalar field, is invariant under P transformation. So let me say invariance. Invariance. If you take scalar field, then the Lagrangian, free Lagrangian is bilinear, right? You have kinetic term, which is 1/2 d phi star, right? And then mass term. And clearly this is invariant under these transformations. Now what is important, what happens with X? Actually, change of the sign of X is not really important, because eventually using Lagrangian we are constructing action, or eventually integrate over coordinates. And this integration over coordinates, it's symmetric, or you can select it symmetric, and therefore this change of the sign within the wave function has no particular consequences. So also Klein-Gordon question, of course, will be invariant with respect to P transformations. again, so what is important here is this appearance of eta, but since it's quadratic in the fields, then it doesn't matter if that is plus or minus. Now, other fields, let's see how other fields are transformed under P. And let us take fermionic field. For fermionic fields, we have psi xt, which go to psi minus xt. And here, in general, we can write some 4x4 matrix, right, since it's our 4 spinor. So what are the properties of this B matrix? And here we can use physical input to fix this matrix B. So first of all, parity transformation should not change spin variables. It doesn't affect spin is invariant, right? Spin doesn't change. And therefore, this matrix should be such that it doesn't change spinorial coordinates. We have this bispinor, and so this B should not change, say, projection 1/2 to -1/2. And therefore, B can be proportional to 1, of course nothing changes, or it can be proportional to gamma 0, because in spinorial representation, gamma 0 is 0, 1, 1, 0. And existence of this 1 means that you do not change, you do not affect spin variables within spinors. So it just inverts bispinor. So it inverts, say, spinors within bispinor, but doesn't change spin variables inside spinors. So there are these two possibilities. And to fix them, again, we can use physics input, because we know how the current should be produced, how current should change under P transformation. So for spinors, the current is given by psi gamma alpha psi. And to have kind of correspondence to what we had at classical level, we need to have no transformation of zero component, but vectorial components of the currents should change the sign. This leads uniquely, and I will not do this on the blackboard, I think you did this probably, right, in the relativistic course, that selects B equals gamma 0. Well, it's clear because you have what? You have here, when you take gamma 0, you have gamma 0 and gamma 0 here, that will not affect. However, if you have here, say, alpha equals 1, 2, 3, then you will need to have additional permutation, which leads to minus sign. So this is how we fix transformations of spinors, and you can check that Dirac equation is invariant under these transformations, and Lagrangian for free fermions is also invariant under this transformation. So B is gamma 0. Now for electromagnetic field, so it's again 4 vector, and therefore for electromagnetic field A0 doesn't change the sign, and other components change the sign. And we say that actually parity of photon is minus. Now we can check invariance of Maxwell equation. Which is equation of motion for vector field. And it has the form A mu xt equals the current. Oh, is that right? Mu current x t. And what happens is that left-hand side doesn't change the sign for zero component, and it changes the sign for vectorial components. So under P transformations, this equation is invariant. So now let us consider interactions. Are interactions invariant or not? And for electromagnetic interactions, we had the Hamiltonian charge. This is one of the terms. Then the field, gamma alpha, psi A alpha. And clearly, this is invariant under P transformations. It is invariant because zero component here doesn't change the sign, zero component of A doesn't change the sign, and vectorial components of the current and the field both change the sign. Okay, so this is also invariant under P transformations. So I can probably, okay, so let me write this still. So the current, so we have here the product of the current alpha multiplied by the field. And then you can see immediately that zero components do not change the sign and vectorial both change the sign, so you have this invariance. This is general property for all the interactions of this type. And for instance, in QCD, we have Lagrangian, which is given by interactions of quarks. With gluon field. And I omit here color indices. So again, this is the same structure, vector current multiplied by vector field, and this is invariant. And therefore, you have also invariance of strong interactions with respect to P transformations. Questions? I think so far I'm just repeating what you already studied before. Okay?
Well, you have a theory where maybe you will discuss it later. You will discuss when we have a Lagrangian that is an invariant under P transformation.
Yeah, so we will discuss later weak interactions,
okay.
And we'll discuss violation of parity. But before this, let me first formulate this on quantum level. So before we essentially used classical fields and classical and just coordinates. Now let me go to quantum level. So, and defining transformations at quantum level, we are using correspondence. We want to have correspondence to what we had at classical level. So, in general, transformations at quantum level are described by the following, described by introduction now of operator of P transformation. And the general form is like this, and so we need to define what is this P. And so that's what we call P. And to match the situation in classical case, this our Fp should be eta P, and then F minus X and T. So which means that P F P minus 1 is eta P F. And I omit here X again, saying that it's not relevant. Probably I will just add that eventually, you see, we introduce Lagrangian, but when we are doing computations in S matrix and S operator, we have integral, right? The X over Lagrangian. And therefore, we can just change the x to minus x in an integration, and that makes irrelevant this appearance of sign minus. Just doing integration over space, so we are kind of eliminating this change of the minus sign here. Now, how this operator P acts on vacuum? Now, it's again the same state if vacuum is invariant. Under P transformations. And therefore, P transformation of a given field is just given by eta P of a given field and F in this case. I don't want to repeat again the things that we did before, so we know how the field is transformed, which is operator. Now the state is produced by acting of the operator on the vacuum state, and remember we did this in last lecture. Showing that action of an operator on the field has such a form. Maybe I will repeat once again. So that we have state F, which is produced by F multiplied by vacuum. Now we know how F is transformed, so that the state Fp equals P F P minus 1, 0, right? So this, we know how this is transformed, and so this is given by eta P F 0. And now if vacuum is invariant, then this is again vacuum state, and that leads to such a transformation of the state. So what I did here, I just showed that this is how the states are transformed under operator of parity. Okay, so that is the transformation again, and this is important if vacuum is invariant. So if you have what we call spontaneous violation of the symmetry, which means that vacuum is not invariant, and for instance in the standard model vacuum is not invariant with respect to symmetries of the standard model, that would not work. And in fact, one of the important mechanisms of parity violation is precisely this non-symmetry of vacuum, of the lowest state, that we will discuss a little bit later. So this is the law again of transformation, P transformations of the states. You can look at this equality in the following way. This is operator. This F is eigenstate of operator P with eigenvalue eta. So our parameter eta, which can be plus or minus, turns out to be quantum number which characterizes a given state, right? And so F is then, in this case, is the eigenstate of operator P with this eigenvalue, which means that eta P is characteristic of the field. Clear? Should I repeat something? No? So again, we introduced the transformations of the fields and then transformations of the states under P transformation at quantum level. Now, if Hamiltonian commutes with operator P, that is P and H is 0, then P is conserved. Sorry. Eta P is conserved. And I will not repeat all this kind of consideration we had before. So again, if P commutes, Hamiltonian commutes with operator P, means that that P is some quantity which is conserved, and which means that eta P is conserved. In a sense that P in initial, eta P in initial and in final state is the same for all the processes. Now for photon, by the way, eta P is -1, which corresponds to transformations of vectorial components of the photon. You can say, oh, why we are not changing, say 0 component, A0. So first of all, you have some relation between components because a photon is massless. Only two are independent. And the second one is, yes, we are introducing it this way. So you can try a different way, then you will get some nonsense. So next topic is parity of the system of the fields. Suppose we have the state which is produced by acting of several fields onto vacuum state. So let us consider this state, which is F1, Fn acting on vacuum. So this state is transformed under P transformation by acting of P onto F1, Fn. So what I'm going to do, I want to introduce the parity of the system of the fields. So I can write this as P F1 Fn 0. And then what I will do, I will insert 1 in between of each of pair of the fields. 1 which is P minus 1 P, as we did also before. So also here P minus 1 P, and also here P minus 1 P. So what I will get is the following, and P minus 1 is inverted operator. So what I will get is P F1, P minus 1, P Fn, P minus 1. Oh, start to put here P and vacuum. Agree? Now, what is this? This is by our definition as the parity of the field 1. And the same as here. Here is the parity of the state n. And now if vacuum is invariant, this is just vacuum. And what we get eventually, we will get eta P1 product Pn, and then our state F1 Fn. Okay, all this P disappear, and then again I get this initial state, which means that the parity of the system of the fields is introduced as the product of parities of individual fields. And so the parity is multiplicative quantum number. So let me remark just immediately, because we will have some quantum numbers which have this additive character. And this quantum number is multiplicative because the generator of the symmetry, it appears here as a just factor. What we will discuss later, we will discuss the transformations when generator appears in the power as a power or in exponent. So this is alpha parameter. So if you have operator which appears in transformations in the exponent, then that will lead to quantum number which is additive. Here you see transformation is just staying here, so this Q here in exponent here is just as a factor. And in this case, you have multiplicative quantum number. Still, there is one point at which coordinates transformations are important. And this is important for orbital motion. So we have the system of the fields. And what we have discussed essentially kind of internal parity, right? But if you have, suppose you have two fields, then for them the change of x, sign of x, becomes important. Because that affects the relative motion of two particles. Suppose you have two particles, A and B. And then under P transformations, they change the position, so it will be B here and A here. And if these two particles have an orbital motion, so they're kind of rotating, characterized by an angular momentum L, then the wave function changes under P transformations in the following way. Psi L minus R is transformed to -1 in the power L. I don't need this. And here will be psi minus R. So not only the coordinate change the sign, but also you have appearance -1 in the power L. L is total orbital momentum. Again, I assume that you have already studied this. And therefore, under P transformations, in general, we have two contributions. One is internal parity, which we have discussed before, and also you need to take into account this -1 in power L, so that we can introduce total parity as -1 in power L, and then the product of internal parities of the fields in both. So now let me discuss conservation of parity, and I will repeat to some extent what I have started with. So let me discuss parity conservation. So again, consider two states, I and F, which are eigenstates of parity operator, so that P acting on I gives eta I, and parity acting on F gives and parity acting on final state gives eta parity final, and this is final. Okay. So let us consider the transition between these two states, final, driven by Hamiltonian of interactions. Then again we can insert here 1, which is P minus 1P, and here is 1 again, P minus 1P, which produce for me the following final state, P minus 1 PH, P minus 1 PI. And now this one is just giving me eta parity final, and final state. Now, if Hamiltonian is invariant under P transformation, then this is by definition is just H, and this gives me eta P initial, and this is initial state. So then what we will get finally is eta final P multiplied by eta now initial, and then final H initial, and therefore to satisfy this equality we need to have, because we have, this is what we started with, right? And after transformation we are getting this, and therefore to satisfy this equality we need to have eta pi f multiplied by eta pi initial equals 1. And since these parameters are plus or minus 1, so you can multiply always by, say, pi from this side, and pi squared is 1, what we will get eta pi f equals eta pi initial, which means that total parity should conserve if we have invariance of Hamiltonian with respect to transformations. Questions?
I think you are pretty proved it in a sense.
Sorry?
At the beginning of the class, you used the commutator of Hamiltonian in some parameter.
Right.
It followed from that immediately.
Sure. I just repeated this, that you can do this in two different ways. Okay? So this is why I have repeated this. And for this is like good that you mentioned it. And that was the reason why I could just refer to it. So now we start to move. Oh no, before this I will probably make one comment. So what is the consequence of parity conservation? Actually there are important consequences which we will discuss to a large extent later. But one of these properties which follow from parity conservation is that matrix elements between states characterized by momentum Pf and lambda f. P initial and lambda initial. So this matrix element equals to the matrix element when we change the signs of all momenta and helicities. Okay, so this is one of the consequences of parity conservation. And there are many important consequences for different processes, because some processes do not exist because parity is not conserved. You need to take into account parity of initial particles and final particles, and total parity should be conserved. So let me now discuss how we established the parities of different particles. And what is important, one of the most important things is to establish parity of pion. Then using parity conservation you can find what are parities of other particles, right? So it's enough to have just one particle, knowing what is the parity of one particle, and then you can reconstruct parities of other particles. In the previous years I did this kind of completely on the blackboard, but now I just give some scheme of how the parity has been established. Very important physics. So, parity of pion. This is also interesting because kind of interesting physics is behind this. So what we are using is to establish parity. Conservation of total parity in the processes. Of total parity. And the second is entanglement of internal parity and the orbital motion, parity related to orbital motion. So entanglement of orbital and intrinsic or internal parities. And remember, eta total is given by minus L and eta internal. I put here P because there is also C parity. We'll discuss it a little bit later. So the process which people use to establish parity of pion is pi minus scattering on deuteron with two neutrons in final state. So this is the process. An actual observation that this process is not suppressed in any way gave conclusion about the parity of pion. So this process, observation. In observation, the experimental result that there is no suppression or cross-section of this process. So it proceeds as it would be just a strong interaction process. The process occurs in two phases. So you have pion, the first phase. You have pion which approaches deuteron, and what it does, it loses the energy radiating gammas, and it forms pi atom. So it's pi minus. So you form the atom, and in which instead of electron you have pi minus. And again you can wonder, so pi is a short-living particle, 10 to the minus 8 seconds. But it is still much more, much longer time than typical lifetime with respect to electromagnetic interactions, which is 10 to the minus 16, 10 to the minus 17, which means that it's 9-10 orders of magnitude, so bigger lifetime of pi than electromagnetic processes, and in particular formation of this pi atom. So it leaves 10 orders of magnitude, 8 orders of magnitude more than formation. So it's big lifetime. It's like a stable particle. So it's electromagnetic radiation and formation of this pi atom, pi minus neutron. The second one, second phase, is due to strong interactions, which is capture of pi. And the radius is small because pi is heavier than electron. So what happens is that pi moving along the orbit around neutron is captured, and then you will have final state, which are just 2 neutrons. So the state formed by pi and neutron has spin 0. For fermions, we are not introducing internal parity, because fermions always appear in pair, right? And therefore it has no physical meaning. You can do this, but it has no physical meaning. Parity of neutron, because of spin, because of orbital motion, is +1. Therefore, the parity of initial state, total parity of initial state, just equal the parity of pi, right? So there is no internal parities of proton and neutron. Parity of neutron, orbital motion, is +1. And therefore this is the initial parity. Final parity, or final state, equals parity of 2 neutrons. Which is given by -1 and then orbital motion of 2 neutrons. Therefore, the parity of pi equals -1 and orbital motion of 2 neutrons. So you need to establish what is orbital motion of neutrons in final state. And for this, what people used is conservation of angular momentum, and Pauli principle. Well, I will not describe all this analysis, but you may get some idea of how it works. So you have 2 identical particles in final state, and therefore the wave function of these particles should be antisymmetric with respect to permutations of neutron and neutron. So that actually imposes the bound on the wave function of 2 neutrons in final state, And then you use just conservation of angular momentum in the process of this capture of pi and production of 2 newtons. And then you will get that this is -1. So the parity of pi is -1. And then using other processes and knowing the parity of pi, you can establish what is the parity of other particles. By the way, it may be even a little bit easy to establish parity of pi 0. Pi 0 has decay into 2 gammas, right? So this has parity -1, this has parity -1, therefore internal parity is plus. So you need to see what is the orbital motion, or orbital external, right, of 2 gammas. And that has been done measuring polarizations of gammas. So measuring polarizations, you can find that they are in the state with the orbital motion -1, and therefore parity of pi 0 is also -1, which is expected, right? Because these guys form isospin triplet with pi plus and pi minus. Okay. So now let me discuss, and by the way, what have been used again that parity of strong interactions is conserved, of course, in this analysis, both in electromagnetic and in strong interactions. So in both phases, parity has been conserved. So now let me start to discuss parity violation. In all the processes due to electromagnetic and strong interactions, parity is conserved. And we saw this also at the level of Lagrangians. We know what are Lagrangians, and you can immediately check that Lagrangians are invariant under P transformations. So now let me discuss parity violation. Who knows the story of this parity violation discovery?
Cobalt atoms at really low temperature.
Yeah, so this is experiment who, which you are saying, but history. So what was, how it was motivated? Yeah. Okay. So that emerged actually with discussing of so-called theta and tau particles. So what are these particles? This is not tau lepton, by the way. So it was an experiment in Brookhaven in 50s, and they used proton accelerator. They use proton accelerator actually he had the name Cosmotron, and they had, the name Cosmotron was that the particles were accelerated at the energy, say 3 GeVs or so, and people were very much excited that they reached this type of acceleration, which is actually comparable with what you have in cosmic rays, so that machine called Cosmotron. This was cyclotron actually, with this kind of spiral trajectories when the field was not changing. What has been discovered, and one of the first discoveries, particles have been discovered, charged one. Further, they were identified with K plus and K minus methods. but this they didn't know. But these particles had decay pi plus and pi 0. And this is theta plus, this particle called theta plus. And tau plus had decay into 3 pions. And these particles had a spin 0, so that initial state has spin 0. Now the parity of 2 pions is +1, right? If they are in state with no orbital motion. But even this doesn't matter, so the knowledge of total orbital motion is not relevant much. Here the parity of these two guys, these 3 particles, is -1. Right? Because you have 3 pions and each has the parity -1. Okay, so 2 particles have been discovered which have different parities, right? So if you assume the parity is conserved, of course, then this is the parity of theta, and this is the parity of tau. The puzzle was, and what is called theta tau puzzle, is that the masses of these particles were equal within the experimental accuracy. This is one thing, but even more striking was that the lifetimes of these 2 particles were equal. And not only this, even cross-sections of production of these 2 particles were equal. And especially this is strange, because masses are equal. Here you have 2 particles, here you have 3 particles, and phase volume in final state is completely different. So one would expect something like 2 orders of magnitude difference in the lifetime, just because of the fact that you have 3 particles here and 2 particles there, and the masses of these particles were around say half a GeV, and 3 pions is already kind of significant mass, is 420 MeVs. Here the phase volume is much bigger, so you would expect that this should have much faster decay than this one. Nevertheless, they established this equality. And as I said, that the number of theta was approximately the number of tau. So that was the puzzle. And so what is the solution? I said already that one of the first who did this proposal was Shapiro. Actually, again, there is some footnote. I never checked this footnote in one of the papers that can be explained by the parity violation, this paradox. But so the credit was signed by T.D. Lee and C.N. Young. They were saying that the following: no, these are the same particle, that theta is tau, and therefore you immediately explain all these features, but parity is violated. So that the same particle, and now we know this is K plus, can decay into 2 pions, and it can decay into 3 pions. Right, so the parity of these 2 guys is is +1 and this is -1, and at least in one of them the parity should be broken. So K has parity -1, so that was established later. But even if you don't know what is the parity, clearly if you have a single particle which has decay with final states with parity +1 and -1, means that you have at least in one mode violation of parity. So the idea was that parity is conserved in strong and electromagnetic interactions, but it is broken by weak interactions. So the conclusion is that parity is broken by weak interactions. And therefore one expects to see some manifestations of parity violation in beta decays, for instance, in muon decays. And actually what is interesting, I was recently, last year, it was a conference on history of neutrinos, and people involved in this kind of studies, still alive, some of them, when I gave the talks. And you know, that what has been established and checked in beta decay. But in muon decays, it's even easy to establish parity violation manifestations. And this has been done literally a few months later after Lee and Young made suggestions and Wu made the measurements. So in principle, if people would have this idea of parity violation, they could, in weak interaction, they could establish this even before all the story. So, well, also in pion decay, and the fact that you have a strong suppression of electron channel is to a large extent related to this parity, V-A structure, which means that you have parity violation. So Lee and Young proposed experiment. And they actually proposed to use beta decay to establish parity violation. So they proposed beta decay. And before I will go to the experiment, let me give you a little bit theory. Actually, we'll have exercise also in this final bunch of homework. Remember that Fermi, and now we are back to our this V-A discussion. In analogy with electromagnetic interactions, proposed the Hamiltonian as the product of vector current and vector current. So this was hadron and this is lepton. And this is P invariant, right? Clearly so. Because we have product of two vectors, zero components again do not change the sign, vectorial components change the sign under P transformation. So that's clearly invariant. Now what is not P invariant? So let us consider axial vector current, which is psi, or fermion fields, gamma alpha, gamma 5, psi. How this is transformed under P transformations. Appearance of gamma 5 and the fact that you need to make another permutation of gamma matrices leads to the following transformation, that zero component of axial vector current changes the sign, it's opposite to vector current, while the vectorial components do not change the sign under P transformations. So here I denote A as a current, so it should be alpha. So if you would have Lagrangian, which is the product of two axial vector currents, that would also be P invariant, right? So what is not P invariant is cross term when you have the product of vector current onto axial vector current. So this product is not P invariant. And again, you will have the exercise to see how this is transformed under P transformation. So that if you have combination V alpha plus JA, the axial vector, multiplied by, this is for hadron, and for lepton we have V alpha plus A alpha, leptonic. So this combination under P transformation is not invariant. So you will check yourself what is the transformation. But again, it's clear that if you have product of axial and vector, this is already not invariant. It changes the sign, right? Under P transformations. So let me now discuss discovery of parity violation. So the idea was to use decay and to study decays of polarized nuclei. That's what we believe Young suggested. So, and what has been suggested to study decay of polarized cobalt 60, which has spin 5. And this large spin nuclei has been selected because it's easy to polarize it. So it decays with final state, nickel 60 plus electron and plus electron antineutrino. And the idea was to study angular distribution of electrons which appear from decays of the cobalt. So that you have cobalt polarized along certain direction. So it has spin, for instance, in Z direction. So this is cobalt 60, and the spin direction corresponds to this type of rotation. So that this is that rotation. And then after decay, you observe electron with momentum PE, and in general it has spin polarization, helicity, and theta is the angle between electron momentum and the spin of cobalt. So, suggestion is that if you have different number of electrons which are going in the upward direction and to down, this is explicit violation of parity. And again, you can wonder, so still you have S which is directed in this way. So why then you have, if you have different you have already some kind of singled out direction. Why difference of fluxes of electrons in this direction and in this one would correspond to parity violation? Do you understand my question? I think in this problem, you still have some direction. You have polarization of nucleon, right? And it's polarized in a certain direction. So which means that that you have some direction still, which is kind of picked out, right? So you have some certain direction in this problem, in this system. So you would expect that what is strange that if number of electrons in the direction of spin polarization of cobalt is more than in opposite direction, vice versa. And let me come back to what we discussed in the beginning. So this is our convention that spin is directed here. In this problem, the problem is completely invariant with respect to up and down initial state. So what we have in initial state, we have this polarization, we have polarization of nuclei, which corresponds again to the motion in the plane. So initial state is P invariant. It is invariant with respect to reflection. Z go to minus Z. Clear? So initial state is P invariant. And of course, if you have in final state the number of electrons going in upper direction and in down direction is different, then this is not P invariant. This is not P invariant. Well, actually, what does it mean? Of course, you have many nuclei. In some nuclei, a given nuclei can decay in both directions with some probability. So this is for decays of many cobalt nuclei. You will have more decays in down direction than in the direction of spin of nuclei. So this is P invariant initial state. Final state is not P invariant if you have such asymmetric situation, which means that you have a violation of parity, and therefore your Lagrangian of interactions should be not P invariant. So Lagrangian should break Lagrangian is not P invariant. You see, it is important that initial state is P invariant, because if this is not invariant, and in final state you have something which is not invariant, then your Lagrangian can be invariant. So what is important that initial state is invariant. Final state is not. And therefore Lagrangian should be not invariant under P transformations. So that would correspond to the situation where the probability of emission at the angle theta is not equal to probability of emission at the angle pi minus theta. Right? So if you have this and these two directions, so this is theta and this one is pi minus theta, then the fact that you have more particles here than there, electrons, means that you have this inequality of probabilities. Now, why polarization is important? Polarization is important to the fact that you want to visualize the effect of parity violation. Briefly, if you would have unpolarized cobalt, then you would have equal number of cobalt polarized in this direction and in this one, right? Unpolarized you can imagine as the state when you have equal number of polarizations in two different directions. So in this case, what you would have, nuclei polarized in this one will give this asymmetry. Nuclei which polarized in opposite way will give opposite situation when more electrons are going up and less down. And when you sum up, you will have symmetric situation. Okay, so this is why polarization is important. Not because you have no parity violation, but because of this kind of summation, you hide the effect of parity violation. And, therefore, and this is the reason why in the early experiments when polarization hasn't been studied, hasn't been used, people didn't see the effects of parity violation. So before, I probably want to do one thing in the, say, 5 minutes maybe. And then I will discuss the experiment itself on Monday. And again, what I will do is the following. Now, if you introduce parity violating Lagrangian, you need to make computations. And you need to find what is the probability and what is this asymmetry. Again, you can do this without any computations. And I hope you will eventually, and sometime probably appreciate what I did, because I kind of explained the results without doing real computations. Again, so when I'm working, I'm trying to do as much as possible before I start to compute something. So that is extremely useful. Now we have Lagrangian, let me remind you. And now we need to introduce some Lagrangian which has no p invariance. Well, in one example, if you add axial vector currents in certain ways, so that Lagrangian is not p invariant. And then it can lead potentially to this type of asymmetry. So knowing Lagrangian, you make computations. And what you find eventually, the decay rate or the probability of the decay as the function of kinematical variables. I have already explained this once before. So in this present situation, you will eventually get the probability as function of momentum of nuclei, spin of nuclei, in general, momentum of electron, spin of electron, and in general it depends also on parameters of neutrinos. So finally, what you compute is some function of kinematical variables. But you can find this p up to some coefficients without doing this quantum field theory computations. So this can be done in the following way. You use some symmetries. Still you have Lorentz invariance. You assume Lorentz invariance. This means that probability should depend not in an arbitrary way on these characteristics, but as in certain combinations, as the scalar products, like Pe spin of nuclei. I don't know, I started to call this nuclei, but we have forward. Let me continue this way. So it can depend on this combination, it can depend on P and spin of electron. It can depend on Pi and P electron. And maybe you can invent something like this. So the statement is Lorentz invariance tells you that these momenta and spins should enter your probability in these scalar combinations. Okay. So now, what are combinations which P invariant and P non-invariant? this combination is invariant or not under P. Product of momentum of electron and spin of nuclei. So it's not invariant. Now this one is also P not invariant. So this is P invariant, right? This is P invariant. Which means that if you have violation of parity, these type of the combinations should appear in your final expression for the probabilities. Now we consider nuclei at rest. And therefore this combination is not even appearing. Now we do not follow we do not follow polarization of the spin. Suppose, and this is what has been done in the experiment, we do not measure polarization of the spin. So we are doing summation of possible polarizations of the electron spin. And of course we do not measure neutrinos. So therefore experiment is not sensitive to this. And the only combination to which your experiment, or this Wu experiment, is sensitive is this one. And therefore on general ground you can write that the probability is given by A plus B Pi. So this is P electron and spin of nuclei. So let me put here, spin of nuclei. So this term clearly will lead to asymmetry, because if P is in this direction is positive, then in this direction you will have opposite sign of this product, right? So in direction up that will be positive, and in direction down it will be negative. Agree? So usually what people are writing here is that probability is proportional to A, here 1, plus alpha cosine theta. That can be written in this way, where alpha is some parameter. This parameter alpha can be computed eventually, right? If you know Lagrangian, then eventually all these computations finally are reduced to just finding what is this alpha. And I think I will probably stop at this point. If, of course, you have no parity violation, then this alpha is 0. So alpha is 0, it's no parity violation. So if your Lagrangian has purely V structure, then you have alpha 0. This you can say for sure. Otherwise, you have this non-zero alpha. So that alpha turns out to be the function of GA. Remember, this is parameter which enters Lagrangian with axial vector current. So if GA is 0, then alpha should be 0. And of course, if also corresponding current in lepton is it. And also alpha should be depending on degree of polarization. So that if you have unpolarized nuclei, then alpha is also 0. So alpha 0 for unpolarized. Questions?
in the final result, I have a combination of a P invariant product and
So invariant enters this A, if you want. So this the first part is invariant, and the terms like these would enter here. Well, it's nice, right? So you can write this already without any computations. You can write this expression. And sometimes symmetry allows even to further advance. And I told you that some years ago it was really this big boom of discussions of these so-called amplitudes, when the idea was to find amplitudes of various processes without computations on the basis of symmetries. If you know the symmetries, here we use just Lorentz invariance, right? And we also use, of course, this parity, because if parity is conserved, then immediately this term should not appear. But we can use some other symmetries also to have big input. Probably even symmetry allows you to somehow connect these two things, but I haven't tried. Maybe you will try. That everything will just reduce to computing of one coefficient. And then for experimentalist who is usually measuring some ratio of different processes, branching ratios, even this will be not important. Okay, so please give me the exercises, and everybody has, right? This, the last. So how was your checks of homework yesterday? Any complaint? No, don't hesitate. Well, so be serious. You can complain to me and about me also. So I will just improve next time. So I need to switch off.